So today we're going to move from the realm of finite probability distributions to the realm of continuous probability distributions. So if you recall, a finite probability distribution is one that's associated with a finite discrete random variable. All right, so a finite discrete random variable. So I usually think of a finite discrete random variable as something that's countable, right? So like the number of summer days that are above 90 degrees, or the number of times you roll a 6 in 6 rolls of the dice, or something like that. Something that's countable. That's what I usually consider a finite discrete random variable. And we can represent the probability distribution for a finite discrete random variable in a histogram. Okay, so we've done that. Histogram. That's what we've done so far. Now we're going to move on to continuous probability distributions, where the random variable is a continuous random variable. So a continuous probability distribution is a probability distribution associated with a continuous random variable. Okay, continuous random variable. All right, so if you recall, a continuous random variable is something that can take on any value, not just discrete whole number values, but it would be something. I think of this, if I think of this as being countable, a finite discrete variable is countable usually. I think of a continuous variable as something that's measurable. Measurable. Right? So it'd be things like your heights or the heights of people, the weights, it could be temperatures or something like that, where the random variable can take on any value. All right, it can take on 2 and 3, but also 2.5 and 2.75 and 2.34689. It can take on any value. And we use something called a probability density function to represent a continuous probability distribution. So a probability density function is comparable to a histogram. It's just that now, rather than the variable taking on discrete values, it can take on any value over the range of values possible for that random variable. Okay, so let's take a look at some properties of a probability density function. So I'm going to call this probability density function f of x. Now you should know that this f of x is not, it doesn't give you the probability. What it does is it gives you probability density. Okay, and that's important because we're going to use the probability density function to find probabilities, but the probability is the area under the curve. Okay, so this the probability, if we want to find probability from the probability density function, we need to find the area under the curve. All right, so the first property is that f of x is non-negative. So the probability density function is non-negative for all values of x, which makes sense because if the area under the curve is the probability, and we know that probabilities are always positive, so it makes sense that f of x would have to be positive because we want positive areas. Okay. The other property is just that the area of the region between the graph of f of x and the x-axis is equal to 1. All right, and that should make sense too, because if the area under this curve is equal to the probabilities, then the probability under the whole function should be 1, because that's just saying that something in that range of x values, or the domain of x values, is going to happen with 100% 100% probability, right? So the area under the whole curve is 1, right? 100% probability, because that's the probability of something happening. All right, so the key thing here is that if we want to, if given a probability density function, we can find the probability of the random variable taking on a value between, say, A and B by finding the area under the curve between A and E, or A and B, A and B. All right, so here the probability that our random variable x is between A and B is given by this shaded region. So this shaded region, if we can find that area, then we'll have the probability. The probability will be that area. All right, that's the key thing about probability density functions. All right, now there's a specific type of probability density function that we're going to be focusing on today, and that's the normal distribution. The normal distribution is particularly important just because a lot of things that we can measure fall naturally into a normal distribution. They're considered normally distributed. And the key thing is that you have, the key things, I should say, is that you have a cluster of values around the middle. Okay? They cluster around the middle and they taper off symmetrically. So that's what this is supposed to be. Symmetrically. The symmetry is very important for a normal distribution. We're going to use the symmetry, the symmetry of the normal distribution can help us solve problems. All right, so that's kind of the key feature. We have the cluster in the middle, and they taper off to zero symmetrically about that middle. Okay, now some examples of natural phenomena that exhibit normal distribution are things like the heights of adult males, let's say. Adult males. All right. If we were to measure all the adult males in a certain population, their heights would be normally distributed. That means that there would be an average. There would be an average height, and then most of the people would be clustered around that average. And then the farther you get away from the average, the less probable those occurrences will be. Okay, things like weights of newborns. Weights of newborns would be another example. Newborn babies. Newborn infants. However you want to say it. A lot of times you've probably heard of the bell curve. The bell curve. That is a normal distribution. The bell curve is a normal distribution. So things like your ACT scores, your SAT scores if you took SATs. So things like that would be normally distributed. All right, so let's take a look. What does this graph look like? All right, there's the bell curve. It's bell-shaped curve. You can see why it's called the bell curve. It has this sort of bell shape to it. And so again, you can see that the values are clustered around the middle, right? And the middle is the mean, right? That's our mean. And then they taper off. Now, we also know, if we know the standard deviation, then we also know that 68.27%, very precise, of the values for this random variable will fall within one standard deviation from the mean. 95.45% will fall within two standard deviations from the mean. And 99.73% will fall within three standard deviations of the mean. Okay? So the normal curve is determined by its mean and its standard deviation. Okay? The mean is going to tell you where the middle is, and the standard deviation is going to tell you how dispersed the data is. So standard deviation. All right, that's what determines a normal distribution curve. So this is just a summary of what I just said. The curve has a peak at the mean, right? X equals mu. Mu is the mean. And the curve is symmetric about the line x equals mu, right? So it's symmetric about the mean. Mu is the mean. The curve lies above the x-axis, right? And we already know that for any probability density function, it has to be non-negative, so it makes sense. It lies above the x-axis, and then it extends indefinitely in either direction. And you can see that it's tapering off to 0 in either direction as well. The area under the curve is 1, right? That's true for any probability density function because there's a 100% chance that something's going to happen. And then we have these very specific percentages for the area under the curve within a certain number of standard deviations from the mean, right? So 68.2% of the area is under the curve is between 1 standard deviation plus and minus 1 standard deviation from the mean, which is essentially telling you the probability. It's telling you that the probability that your random variable takes on a value between plus and minus 1 standard deviation from the mean is 68.27%. And so on for 2 standard deviations from the mean. We will have 95.45% probability that our random variable will be within 2 standard deviations from the mean, and so on. All right, so let's take a look at example 1. We're going to use what we just learned to find some probabilities. All right, so the distribution of scores for a certain standardized test are normally distributed around a mean of 450 with a standard deviation of 25. And if 1,000 students take this test, how many would be expected to fall within the range between 425 and 475? So the key thing to recognize here is if our standard deviation is 25, then these values, 425 to 475, are essentially 450 plus and minus 25, which is the standard deviation. So these are the scores that fall within 1 standard deviation from the mean. And so we know that 68.2%, right? So 0.6827, if I express it as a decimal, 68.27% of the scores will fall within that range. So 68.27% of 1,000 students gives us 682.7 students. So we would expect that 682.7 students, we can round that up to 683 because we really can't have a 0.7 of a student. So we'll round it to 683. So 683 we would expect would have scores within that range, within 1 standard deviation from the mean. Okay. All right, so how many scores would we expect to fall between 400 and 500? Well, again, we need to look at how, these are, if we take the average of those two, we get 450, right? So this is essentially 450 plus and minus 50, right? Which is 2 standard deviations. So this is 2 sigma, right? This was 1 sigma, one standard deviation. This is now within 2 standard deviations from the mean. And if you look back at the graph that I just had on the previous page, we said that 95.45% of the area is between 2 standard deviations from the mean, which means the probability of falling within 2 standard deviations from the mean is 95.45%. So 95.45% of 1,000 students would give us 954.5 students, right? Or probably better to just write it as 955, okay? Because we don't really want to have a fraction of a student, all right? All right, so this next one's a little tricky. How many scores would we expect to fall above 500? Okay, so we already know that 500 is essentially 450 plus 2 standard deviations. Okay, So let's draw a little picture of what this looks like. So there's our normal distribution centered at 450, and I've sketched in where 500 is, right? 2 standard deviations above the mean. And what I'm interested in, what I want to know is what's this area that I've shaded here. All right. Now, given what I know so far, I know that I know this probability, right? I know that the probability of falling within 2 standard deviations of the mean is 95.45%. So what I can do is I can subtract that from 1. And what I will be left with is basically double what I want, right? If I take the whole 100% or 1, the area of 1 under this curve, subtract out what I've shaded here, the percent that falls within 2 standard deviations of the mean, what I will be left with will be what I want plus this, that's supposed to be blue, plus this little blue area, okay, which is essentially what I want, but it's twice what I want. Because of the symmetry, right, the area from 500 to infinity is the same as the area from 400 to negative infinity. All right, so the probability that my random variable is greater than mu plus 2 sigma, the mean plus 2 standard deviations, which is what I'm interested in, or that the random variable is less than the mean minus 2 sigma is equal to the area under the entire curve minus this area that I've marked in red, which we know is 0.9545. Okay, so if I do that calculation, what I get is 0.0455. Okay, so that area is double what I want because of the symmetry, because it includes both the area that I want. This is the area that I want. This is the area that I that I don't want, right? I don't really care about that area. I just want to know what's the probability of my random variable being greater than the mean plus 2 standard deviations. All right, so what we're going to do is just cut that in half. So the probability of what I want, which is x is greater than the mean plus 2 standard deviations, is just going to be 1/2 of this 0.0455. Okay, when I get that, when I do that, I get 0.02275. All right, so that's my probability of a score falling above 500. And so if I have 1,000 students, then I'm just going to take that probability, 0.0275 times 1,000. And so I would expect on average about 22.75 students, or let's say 23. Whoops, 23 students would have scores above 500. All right. All right, so I think that's enough for this video. This video got kind of long. I will meet you in the next video.